Hi guys, welcome back to the channel Eat Code and Sleep. And today's problem is out of boundary paths. Okay, and this problem is asked by Amazon. Amazon, and let us quickly dive into this problem. There is an M into grade, M into N grade with a ball. Okay, with the ball there is a grade with dimensions M into N, and the ball is initially at the position start row and start column. Okay, it is initially at that position, at that particular position. Okay, you are allowed to move the ball to one of the four adjacent cells. One of the four adjacent cells means you can move the ball from the starting position to the up position or the down position or the left position or the right position, right? So from here you can move here, you can move here, you can move here, or you can move up, right? So these are the four adjacent paths you can move the ball. So okay, and four adjacent cells in the grid, possibly out of the grid crossing the grid bound. Okay, let us visualize this statement here. Okay, you can apply at most max moves. Okay, you have to apply only max moves to move the ball. Okay, from starting position to any position you can move at least max moves, right? So uh, you can move at most max moves, right? Okay, and given the five integers m and m is the number of rows and n is the number of columns and max move is the number of moves you can move from the start position to the this another position, and start row and start column are given. Okay, return the number of paths to move the ball. Okay, to move the ball out of the grid boundary. Okay, so what we need to do is from start position we have to we have to move the ball such that it goes out of boundary. Okay, so whenever it goes in out of boundary, then it is a valid path. Okay, so this is what the question is saying. So and what are the crucial points here is we have to keep track of the we have to keep in mind that it has to go to out of bounds and it has to go only max moves from the start position. Okay, and these conditions has to be keep in mind. Okay, so this is a simple recursion, right? As we have four choices here, we can go from left, from starting position to left, like this thing, and from right we can go right, we can go down, we can go left, up, right? So we'll simply apply recursion here, and after applying, whenever we go to a move, we will do our max moves minus one, so that we don't exceed our max moves. Okay, so whenever our max moves comes to zero, then we can know that uh, we have traveled max move, so we have to not travel more than that, right? So we have to not travel more than that. Okay, and this is what we will be doing, and initially we will be at the starting position and starting column, right? Starting position, right? From that position only we have to move the ball. Okay, such that it goes out of bound. So how many parts it goes out of bound, right? We need to return the answer, right? So for example, the ball is here, so it can move up in one move, yes, and it can move left, right? So it can if it moves up it goes out of boundary, right? And if it moves left it goes out of boundary, right? Or else it can move here and here, right? It goes out of boundary. Or it can move here and here, right? It goes out of boundary. And it can move here and here out of boundary. And it can move here and here. Right? As we can see here, the max moves are given as two only, right? So at most we have to apply only two max moves, right? So that's why we are not going in this path. Carefully observe. So in this path we are not going. This takes around three moves, right? This takes three moves, so we are not going in that path. So we have to not consider that path as a valid path. Okay, so whatever the moves we are moving, it should be at most max moves. At that in that path only we can consider as a valid path. Okay, and it should also go to the out of bound condition. Okay, so this is what the question is, and let us visualize another example here. So here we can move three. We can move at most three moves. Okay, so from here I can move out of bounds. I can move out of bounds in one move only. So from here I can move in one two moves. I can move out of bounds, and two moves I can move out of bounds, and two moves I can move out of bounds. And from here also I can move out of bounds, and now can move out of bounds. I can move out of bounds in two moves only. So and in how many in three moves how can we move? So I can move left, and I can move again right, and I will move up. Okay, in three moves I'll be moving, and I'll be moving left, and I'll move again to the right, and I'll be going down. So this is the three moves path again. So this is also same. We'll go right first, and we'll come left first, left, and we'll go up, and this it turns to three moves, right? So it is lesser than or equal to max moves here. Okay. So and we go to right, and we come right, and we go down here, and this is also comes to three moves only. So this is how we'll be moving around the moving from the starting position to the out of bound condition. So let us quickly solve this recursive solution. Okay, as we can see that the uh, the m and length are 50 and 50. Okay, so we need to apply. So let us quickly apply recursion also here. So what it will, so let us take as the, so the question says that the answer may be very large, so we have to return the modulo, right? So we'll take the modulo here. Okay, we'll declare modulo as a global variable here. Okay, 1 2 3 4 5 6 7 8 9. Okay, 9 digits, and we need to call a recursive function here. Okay, so initially it will go from starting position, right? So we'll max move start row, comma, start column, right? Percentile and mod, right? So we'll call this function int solve and int comma int, and let us copy the above thing only. Let us copy those, right? uh, right, and if our starting row, right, so what will be the base condition here, if at all our starting rows, so what will be our base condition here? So if our starting, if the ball goes to out of bounds, and the ball goes in lesser than or equal to maximum rule, right? And the maximum moves will be greater than or equal to 0. So if the maximum moves are greater than or equal to 0, then we can say that the path is in the the maximum moves path only, right? So the number of moves the ball took to go to the out of bound condition is lesser than equal to max moves only, right? So, so this is how we'll be solving this problem, and let us quickly write the base condition here. So what will be the base condition? If start row, so if start row is lesser than 0, or start column is lesser than 0, or and if start row equal to m, or column equal to n, and uh, what is the max move, right? Max move is greater than equal to 0, then we can return 1, right? So here we will return 1 here. Okay, so and one more base condition is, if our max moves is less equal to 0, then we need to return 0, right? So we cannot go further from that, right? So if our max move come to 0, then we don't have any moves to move our ball, right? So from there we can return 0, right? So here max move equal to 0, then return 0. Okay, and the base conditions are set here, and now we'll calling our recursive calls here. So I can go left, right? So from starting position I can go left. So how many paths are there when I go left? Okay, uh, max move. So as I am moving one move, right? So I need to subtract one from the max moves, right? So I'll subtract it, and start row will be same, and start uh, column will be will goes to -1, right? So as we are going left, so our column index will decrease, right? So I have decreased this, and as the same, and where I can go also left, right. So I'll go right here, okay. And if I go right, our same, and macro will decrease to 1, and start row will be same, and start column index will increase, right? When I go to right, column index will increase. So after going left and right, I can go up, right? So I can go up, so I'll write up. So while going up, our column index will be remain same, but starting row will decrease. Yes, starting row will decrease, so we'll decrease our starting row. So I can go down here. After going up, I can go down, right? So going down means increasing the row index, right? So I will be increasing the row index. So here I'll be returning the sum of those, sum of those. So sum of these, right? Sum of these parts, right? This function, what this function returns? How many parts are there when I go left? And this function, how many parts are there when I go right? When I go from starting position to right, okay? How many parts are there when I go from starting position to up, right? How many parts are there when I go starting position to top? So we need to add this all, right? So we will be adding this all, okay? So as the answer can be very big, so we need to return mod here, okay. We need to do percentile mod here, and so we need to do percentile mod here, and okay, and left plus right percentile mod plus up plus down percentile mod and percentile mod. Okay, this is the answer we written. So let us quickly run this solution. Let us see whether our recursive solution is working or not. Okay, here I think I'm doing something, so I'm not doing anything here. So M and N. So what this is? Return. Okay, okay. Column, right? So I forgot to return column. And let us quickly run this. So it is successfully running. So as the constants are more, right? It is going up to 50. So what will be the time complexity here? 4 into 50, right? So as we are having four choices, so it may go up to four choices, and it may go 4 into 50. 4 to the power 50 means so much of complexity, right? So we need to decrease the time complexity. What will be the ultimate optimization of recursion? DP, right? So we need to apply here DP. So I'll be applying here memorization. Okay, so for memorization, what are all the how to select our DP? By checking the parameters. So whatever the parameters are saying, uh, that much DP we need to take here. So here starting row will change, and max move also will change, and start column also will change, right? So we need to take 3D DP here. So we will take 3D DP. Okay, and what will be the length? Length of the DP will be M, as we are at only starting row, right? So it will be M, and uh, for starting column it will be N. Okay, right? The maximum length, right? So and for maximum, as we can go to 0, right? So we need to take maximum plus 1, right? So this is how we'll be taking the length of the DP here, and we'll be applying DP here. Okay, so I will pass the parameter as a DP here. Okay, DP parameter as passed, and here also will let us pass the DP parameter. Okay, we passed. After checking the paste condition, what we need to check whether it is present in DP or not. Okay, so before representing in dp, so we need to turn all the values of dp into -1, right? So we will be doing that thing here. A equal to dp, and for b belong to a, arrays dot fill a comma -1, right? So this is how I'll be filling all the values of dp to -1. Okay. Now my dp is filled with -1. So I need to check. So if my dp value is not equal to -1, then I can say that there is a valid answer there. So I just need to return that, right? So I'll check whether dp of start row, start colum, start column, and max move, right? So is not equal to -1, then I can return, right? So I can return dp of this only, right? So I'll be returning this one, right? And what I need to do, I need to store that answer in my dp, right? So I'll be storing that answer in my dp. So this is I'll be applying the dp here. So let us quickly run this problem. So let us check whether it is running successfully or not. I think I haven't passed the parameters. Uh, Let us pass the dp parameter here. Okay, and here also dp, and yep, I have passed the parameters of dp, and let us now run the problem. So what it is saying, arrays dot fill. Okay, okay, we need to pass here b, right? We need to pass here b. So let us quickly run this. Right, it is accepted. So let us try to submit it. Okay, our solution has passed. So this is how we will be solving this problem. And coming to the time complexity of the problem, so as we are going to every part of the every part of the uh, every part of the grid, right? So we are, as we are going to every part of the day grid, and we are also going to, and we are only moving max moves, right? So what we need to do here, and we are only moving max moves here, right? So every part of the grid into max moves, right? So what will be the time complexity here? Big O of n cube, right? So m and n and max move also can be same, right? So m into the, in at the worst case, what will be the time complexity here? So at the worst case, the time complexity will be big O of m into n into max move, right? So this will be the time complexity, and space complexity will also be same here, right? Big O of m into n into maximum, right? So this is what the time complexity and space complexity. And earlier our time complexity was 4 to the power 50, right? So 4 to the power of 50 was our earlier time complexity. Now we have reduced our time complexity to, at worst case, n cube, right? So if m equal to n equal to maximum, then it will be n cube, right? So we have reduced our time complexity to n cube. So this is what the power. This is the power of the dp here. So we can turn any big time complexity to small time complexity, right? With by using db here, so dynamic program. So this is how we'll be solving this problem. And thanks for watching. Subscribe to the channel, and thank you.